Hello friends, first of all, welcome to all of you for being here in my channel. Today we are going to discuss on a chapter of Engineering Mathematics, semester 3rd, that is Finite Differences, part 1st. In this part 1st, we are going to discuss on the various difference operators. So let's start. We introduce the idea of finite differences and associated concepts which have important application in numerical analysis. For example, interpolation formulas are based on finite differences. Through finite differences, we study the relation that exists between the values that are assumed by the functions whenever the independent variable change by finite jumps. Our next point is that difference operations. There are three difference operators, namely as forward difference operator, backward difference operator, and central difference operator. Out of this, there are again two difference operator exist, that is shifting operator and averaging operator. But in this session, we are going to study only these three main operations or operators, that is forward, backward, and central difference operator. So, forward difference operator means consider the function y is equal to f of x. Suppose we are given a table of values of the function at the points x0, x1, x2, x3 up to so on xn, whereas x1 is equal to x0 plus h, x2 is equal to x0 plus 2h, x3 is equal to x0 plus 3h, like this xn is equal to x0 plus n time h. It means that all the values of x are equispaced. Let f of x0 is equal to y0, f of x1 is equal to y1, f of xn is equal to yn. Then we define forward difference operator, which is denoted by delta. We define delta f of x is equal to f of x plus h minus f of x. Here, this forward operator delta, when operate on f of x, it gives the difference between the next value of f of x and the value itself f of x. Thus, delta y0 is equal to f of x0 plus h minus f of x, which is equal to f of x1 minus f of x0. So, from given, we can write this as y1 minus y0. That is, f of x1 is equal to y1 and f of x0 is equal to y0. So, we can write the subtractions of f of x1 minus f of x0 is equal to y1 minus y0. Therefore, we can write delta y0 is equal to y1 minus y0. Further, x0, x1 up to xn are called arguments. The corresponding values of f of x are called entries, and h is called the interval of differencing. Similarly, we can write delta y1 is equal to y2 minus y1. In general, delta yn minus 1 is equal to yn minus yn to the base n minus 1. It means that when a forward operator operate on any function, it gives the difference between its next value and the value itself. So, delta is called the forward difference operator, and delta y0, delta y1 up to so on delta yn minus 1 are called the first forward differences of the function y is equal to f of x. The second order differences of the function are defined by delta square y0, which is given by delta y1 minus delta y0. Here we have to operate delta on y1 minus again we have to operate delta on y0. Then we get delta square of y1 is equal to delta y2 minus delta y1. Similarly, delta square of y2 can be written as delta y3 minus delta y2. In general, we can write delta square of yn minus 1 is equal to delta yn minus delta yn minus 1. Similarly, higher order differences can be defined. In general, the nth order differences are defined by the equation delta raised to n yi is equal to Subtract the power of delta by 1, then we get delta raised to n minus 1 yi plus 1. It means that the next value of yi, which is denoted by yi plus 1, minus delta raised to n minus 1 yi, means the value itself. These differences of the function y is equal to f of x can be systematically represented in the form of the table called forward difference table. Here you can see the given table is called as forward difference table. We construct the difference table for any number argument, and sample difference table is given for 6 consecutive arguments. Here are x0, x1, x2, x3, x4, x5 are 6 arguments. The corresponding values of y with these arguments are denoted by y0, y1, y2, y3, y4 and y5. In third column, we write here the first forward difference of y. So delta y0 stands for the difference between y1 minus y0. It means that second value minus first value. The next first forward difference operator is denoted by delta y1, and it is the difference between third value of second column minus second value of second column. It means y2 minus y1. Similarly, delta y2 is equal stand for y3 minus y2, delta y3 stand for y4 minus y3, delta y4 stand for y5 minus y4. Similarly, the second order, third order, fourth order and fifth order forward differences are shown in this given table. After this, in the above forward difference table, y0 is known as the first entry, and delta y0, delta square y0, delta raised to 5 y0 are called leading differences. Means each value of each first value of each column is called as leading differences. So, since each higher order difference is defined in terms of previous lower differences, by continuous substitution of each higher order difference can be expressed in terms of the values of the function. Thus, delta square y0 is equal to delta y1 minus delta y0. Now operate delta on y1, similarly delta on y0. It gives y2 minus y1 in first bracket, minus in second bracket when we operate delta on y0, it gives the difference between y1 minus y0. So after simplification we get y2 minus 2y1 plus y0 for delta square when delta square operate on y0. Similarly, delta cube of y0 is given by y3 minus 3y2 plus 3y1 minus y0. Here we observe that the coefficient occurring in the right hand side are simply the binomial coefficient in 1 minus x raised to n. Hence in general we can write delta raised to n y0 means nth order forward difference of y0 is equal to yn minus nc1 yn minus 1 plus nc2 yn minus 2 minus plus and so on minus 1 raised to n y0. nc1 it is the notation of combination, nc2 also up to so on minus 1 raised to n y0. This is the general formula for nth order forward difference when operate on a function y0. Now backward difference, it is second difference operator. Consider the function y is equal to f of x. Suppose we are given a table of values of the function at the points x0, x1, x2 up to xn. All these values are equispaced, means there is a common difference between each values of x, and the notation of y0, y1, y2 up and yn are f of x0, f of x1, f of x2 up to so on f of xn. Then we can define the backward difference operator, which is denoted by and read as a nabla of f of x, which is equal to f of x minus h. Thus the first order backward differences of y1 is given by del nabla y1, and it is the difference between y1 minus y0. Similarly, nabla y2 is equal to y2 minus y1, and in general nabla yn is equal to yn minus 1. Delta is called backward difference operator and nabla is called backward difference operator, and nabla y1, nabla y2 up to nabla yn are called the first order backward differences of the function y is equal to f of x. The second order difference of the function y is equal to f of x are defined by nabla square of y2, nabla square of y3, nabla square of y4 and so on. So nabla square of y2 is defined as is equal to nabla y2 minus nabla y1. Nabla square of y2 is equal to nabla y3 minus nabla y2. Similarly, nabla square of yn is equal to nabla yn minus nabla yn minus 1. Similarly, higher order differences can be defined in general. The nth order differences are given by nabla raised to n yi is equal to nabla raised to n minus 1 yi minus nabla raised to n minus 1 yi minus 1. Here we can see the difference table called as backward difference table. These differences of the function y is equal to f of x can be systematically represented in the form of the table called backward difference table. First column stand for arguments, second column stand for the corresponding values of function y. Then in each column we write first order backward difference, second order backward difference, third order backward difference, fourth order backward difference and fifth order backward difference by using the formulae which we have already discussed here. See, as in the case of delta, we can prove that nabla is also a linear operator. Here is one remark: the relation between two difference operator is given by nabla of f of x plus h is equal to delta f of x. For nabla f of x plus h, we can write f of x plus h minus f of x, and for this subtraction or this difference is also write as delta f of x. Similarly, we can prove this relation for second order differences like nabla square f of x plus 2h is equal to nabla of f of x plus 2h minus the previous value of f of x plus 2h, that is f of x plus h. Take a difference between these two terms. Again, operate nabla into the bracket on each term separately. Then in second step we can write nabla of f of x plus 2h minus nabla of f of x plus h. Because of nabla is a linear, so we can write or operate it on a separate term. Therefore, from this we can write the second step in the form of forward difference operator, that is delta of f of x plus h minus delta f of x, which can be written as delta of f of x plus h minus f of x. So we can easily prove this relation, that is nabla square of f of x plus 2h, which is equal to nabla delta square f of x. In general, nabla of f of x plus nh is equal to delta square f of x. Hence, from the forward difference table of the function f of x, we can obtain backward differences of all orders. Now our third difference operator is a central difference operator. Sometimes it is convenient to employ another system of differences known as central differences, and we define central difference operator, which is denoted by small delta, as small delta f of x means central difference of f of x is equal to f of x plus h by 2 minus f of x minus h by 2. This difference gives us a central value from f of x plus h by 2 and f of x minus h by 2, and which is denoted by, or the value in between these two terms is f of x. So we derive this formula of central difference: small delta of f of x is equal to f of x plus h by 2 minus f of x minus h by 2. Thus, if f of xi is equal to yi, then we have small delta y of y to the base 1 up means small delta y 1 half is equal to y1 minus y0. Y to the base 1 half is the central value from the values y1 and y0. Similarly, the central value of y2 and y1 is y to the base 3 by 2. So, in second step, we write here small delta y 3 by 2 is equal to y2 minus y1. In general, we can write small delta yn minus 1 upon 2, which is equal to yn minus 1. Here the subscript of delta y is the average of the subscript of the two members of the difference. The higher order difference can be defined similar to forward and backward differences. Here, in first step, delta square of y1, small delta square of y1, it means the second order central difference of a function y1 is given by delta y3 by 2 minus delta y1 by 2. Similarly, delta square y2 is equal to delta y5 by 2 minus delta y3 by 2. And in third step, delta cube y3 by 2 which is equal to delta square y2 minus delta square y1, etc. When we take a difference between any two terms, then the central value of that two terms is a central the central value is these differences of the function y is equal to f of x can be systematically represented in the form of the table called central difference table. As we prepare the difference table for forward operator and backward operator, we can prepare easily the difference table for central difference order operator. These differences of the function y is equal to f of x can be systematically represented in the form of the table called central difference table. In first column, we write the values of arguments. In second column, the values of function corresponding to each argument. Then in third column, small delta means first order central difference. In fourth column, delta square y means second order central difference. Next, third order central difference is denoted by delta cube y, and next delta raised to 4 of y means fourth order central difference. The process is as same as for the difference table, which will be already discussed in forward operator and backward operator difference table. Here we have to take the subtraction or take the difference between y1 minus y0 denoted by delta y1 by 2, y2 minus y1 denoted by delta y3 by 2, then y3 minus y2 denoted by delta y5 by 2, and in last y4 minus y3 denoted by delta y7 by 2. Similarly, take the differences between each two consecutive terms, that is next term minus previous term. We can prepare easily this central difference table. With this point, we are going to stop this session here. Thank you.